Okay. Okay. So, hello everyone. My name is Amin Jafarimoghaddam, a fourth year PhD student under the supervision of Professor Manuel Soler. And my thesis is on commercial aircraft trajectory optimization using mathematical and computational optimal control. So, as you can see, the thesis is in the direction of theoretical optimal control. So, let's get started. Okay, I have divided the contents into four categories, as you can see. First, we start with the motivation and problem statement, and then I go to main contribution of the thesis, and then I will present some highlights of one of my latest contributions, and then I will give a brief summary of research activities and outputs. Okay, so for the motivation, we start with the formulation of a trajectory optimization problem in a Mayer format. And as you can see, we have an objective function, and the objective function is based on the value of the final values. And then we have the problem is subject to state dynamics, and in general, state dynamics can be non-autonomous. And then the problem is subject to some constraints, equality constraints, or boundary conditions, together with some state and control inequality constraints. There are different methods and algorithms to solve this optimal control problem. So one of them is first order direct parameter optimization method, which is also called a direct numerical method. The other is based on Pontryagin maximum principle, which is also known as PMP algorithm or indirect analytical method. And we also have dynamic programming in classic or approximate forms using Bellman principle of optimality. We have meta-heuristic techniques like particle swarm optimization and genetic algorithm, simulated annealing, and so forth. And we have Minimax method, which is actually based on the principle of game theory and some other auxiliary theorems. And then we also have learning-based methods, such as reinforcement learning and those incorporating ordinary neural ordinary differential equations or neural ODEs. And also some algorithms, learning-based algorithms that use some general neural approximators. So the direction of thesis is now shrunk down to the first two highlighted methods that we call indirect and direct methods. So for the direct method, we first transform the problem into a nonlinear programming. And this is based on a nonlinear solver together with a control parameterization technique. And after we have a nonlinear programming, or when the parameter optimization problem is formed, then it is patched to, typically it is patched to an optimization module, which solves KKT system. And this involves using methods like interior point methods, IPOpt, and sequential quadratic programming, and so on. And for the indirect method, first we form the Hamiltonian, and we augment then the Hamiltonian with direct adjoint method to incorporate the state inequality constraints. And then by minimization of the Hamiltonian, we can find the optimal control. So for the commercial aircraft trajectory optimization problem, the basic problem, the most basic problem, but yet the complete format of the problem includes at least 5 states. And the problem is to move the trajectory from the initial state to the final state while minimizing a certain objective function. And the controls that are responsible for taking action in time are throttle setting, denoted as pi, and heading, denoted as chi, and then aerodynamic path angle. And the last two controls, heading angle and aerodynamic path angle, are also interchangeable with the bank angle and lift force, respectively. And then what makes the problem so difficult is because the function f contains terms such as wind with substantial, considerable uncertainty, and then the function f is highly nonlinear because it is composed of compressible drag force. And then the problem comes with 3 controls, including singular controls, which makes the problem even more complex. And then flight-sensitive areas add more levels of complexity into the system. So, because of lack of mathematical breakthroughs and understanding about the structure of this specific optimal control problem, the research was, or the thesis was initiated. So, main contribution of the thesis. So, I start with per-tube analytic direct transcription for optimal control, or in short, PODUC. And this is actually a new transcription method based on 2 building blocks. One of them is segmented Hadamian decomposition method to discretize the state dynamics, which is actually a nonlinear solver, and which is responsible to transcribing the NLP, or nonlinear programming format. And then we have the other building block known as average nonlinear programming, or ANLP in short, to discretize the control variables. So ANLP is in fact a control parameterization technique. So the inspiration behind SADM was an earlier method called optimal decomposition method, ODM, that we published earlier, but in order to make it more suitable for transcription, for a more general method that we could apply as a transcription method, we moved to SADM, or segmented Hadamian decomposition method. And the ANLP, both ANLP and SADM concepts are published in the main PODUC paper, but we have also extended ANLP for a practical example concerning applicability of Zermelo's equation to aircraft trajectory optimization, and the concept is also more highlighted in that paper. And then after describing PODUC, we compared PODUC with some other transcription methods and verified that for some, in some certain aspects, such as computational time, such as sensitivity to the initial guess, and so on, PODUC outperforms other transcription methods, such as trapezoidal, Gauss-Labato method, Hermite-Simpson, and so on. But in order to verify the accuracy of the PODUC, we needed to compare it with some benchmark solutions, which were actually non-existent at that time. So that motivated another direction of research, and we eventually ended up with indirect bank singular algorithm, or called IBSA, which is a new indirect method based on the PMP principle to solve any optimal control problems that contain singular controls. So then we applied IBSA for some special cases of IBSA for a general indirect computational framework, which is suitable for vertical flights, in another paper, and then indirect optimization of a complete cruise flight, and then eventually indirect optimization of complete cruise flights with avoidance of flight-sensitive areas and Mach inequality constraints, which is the topic that I'm going to dedicate the rest of the presentation to it. So we consider, for this example,
you have 1 minute and a half.
Okay. So we have an objective function here to minimize, and this is for a cruise flight in a horizontal plane, and we have the familiar system dynamics for that, and then the problem is subject to controlled bounds and state inequality constraints. And then we have a specific way of simulating wind, and then the problem also includes flight-sensitive areas in elliptic formats, general elliptic formats. So for the solution and comparison with the PODUC method, we can see that both methods can actually they correspond to each other, and they agree quite well. And when we compare the final outcome in the table, minimum objective, final mass, and final time, we see that both methods agree up to 3 to 4 decimal places. And then one of the application of the IBSA is its applicability in Monte Carlo simulation because of its remarkable speed. The speed of the algorithm is within milliseconds. So for this, we have solved the same problem, the same cruise problem, but with varying wind to see to quantify the uncertainty within the wind, which is actually quite useful for robust optimization of the problem, including wind. So, and then we get this PDF probability distribution function, which is quite useful for, again, quantifying the uncertainty of wind. And at last, I'm giving a brief summary of my research activities and outputs, papers that you have already seen, and conferences. And I've presented a paper in the IEEE conference on decision and control, CDC, in Singapore. And then research stays, I was at the Department of Applied Mathematics, Scientific Computing Group, Kaiserslautern in Germany, and I was working on emerging methods in machine learning, specifically neural ordinary differential equations. And my current status is hopefully depositing my thesis and participating in Econ Trail project. Thank you for your attention.